Jai Hind everyone. I am Achintya Pandey as an assistant professor in Department of Information Technology at Ajay Kumar Garg Engineering College. Today I will discuss traveling salesman problem, right? Okay, so what is traveling salesman problem? Um, in graph, this is one of applications ki how all the city could be visited once, having least cost. That problem is called traveling salesman problem. So the problem is, this is the problem statement of traveling salesman problem. If there are n cities and cost of traveling from any city to any other city is given, okay, then we have to obtain the cheapest round trip such that each city is visited exactly once, returning to starting city, complete the tour. Means if there are so many cities and we want to visit to all city exactly once, right? So that the cost of visiting all cities should be least and return to the same place where we started the journey, then this scenario, this problem, this whole problem, how to sort out, how to do this thing is under traveling salesman. Okay, so here is a salesman which start visiting from say one city, for example any node say A, and starting visiting all. Okay, so there will be state space tree. Out of that state space tree, which branch we follow so that all node will be visited and the cost must be minimized. Okay, so typically traveling salesman problem is represented by weighted graph. Okay, of course if there will their weight will be given, then and only we can find the cost or overall weight, so that we can get the minimum weight. Okay, so what is the process? There are so many methods to do this problem. Here we will show an example, and to do this we will adopt, we will take the branch and bound method to visit and find the minimum cost. Okay, so to understand solving of traveling salesman problem using branch and bound approach, we will reduce the cost matrix M by using formula like this. Okay, so first we will maintain a cost matrix, or we can say distance vector matrix. Okay, distance matrix. Okay, we will write, and how we find the reduced matrix we will see. So how we will reduce the entry? So this formula we can use in row and column everywhere. Reduce row equal to Mij. Mij will be the entry, ith row jth column entry minus minimum Mij, right? So in the row which will be minimum, every element of the particular row will be subtracted, that we will see. Okay, so Mij minus minimum Mij, where j belong to j from 1 to n, means particular ith row. Okay, and j equal to 1 to n means first column, second, right, third, fourth, and so on. So similarly, column minimizations, we will find the minimum entry. When we will see the minimum, if in the rows either all infinite entry are there, or at least 1 0 are there, is there, then there is no need to reduce that particular row. What is that? Means in the row and column, if all the entry are infinite or there is 0, then we cannot, we have not. Okay, we will see the example, then we will find. So column matrix is just similar to as a row minimization. Column minimization is just similar to as row minimization. In that we will find the minimum element, and out of the minimum we subtract all, I mean, column element to get the reduced matrix. Okay. So full reduction, let M be the cost. Yes, let M be the cost matrix for TSP. TSP means traveling salesman problem for n vertices. Then M is called reduced if each row and each column consists of entire entity, infinite entries, or else contain at least one zero. Reduced matrix means all rows should contain all infinite entry or zero. If it is not so, then we find the minimum element. If all the entry are not infinite or at least one zero is not in a row or column, then what we do? We find the minimum element out of the row or even out of the column, and from this minimum element, every element of the row and column get subtracted. After that, the matrix which we will get, that will be the reduced matrix. So the full reduction can be achieved by applying both row reduction and column reduction. Okay. So row reduction and column reductions are applied to get the reduced matrix. Better we can understand this by some example. Dynamic reduction. Using dynamic reduction, we can make the choices of edges I, j with optimal cost. Okay. Step in dynamic reduction technique. These all are the steps of dynamic reduction technique. First, draw a space tree with optimal cost at root node. What will draw? A state space tree. A tree will be drawn from where the salesman just started and just visiting all. Again we do the same. Okay. So that space tree with the optimal cost at root node will be drawn. Obtain the cost of matrix for path ij by making I row and j column entries as infinite. Also set mij equal to infinite. Cost corresponding node x with path ij is optimal cost. Is optimal cost plus reduced cost plus mij, that we will see. Set node with minimum cost as E node and generate its children. Repeat step 1 to 4 for completing tour with optimal cost. Okay. So just see the steps. This traveling salesman problem can be better understood by the example. Say this is the graph, or we can assume that there are 5 cities A, B, C, D and E. Okay. The cost from a distance, we can say, from every node to all other node are given, and that's why it is called weighted graph. If the graph will be weighted, then and only we can get the reduced matrix, or we can find the minimum root. Okay. So TSP will be only for the weighted graph, right? So what is the processor? The methods are written here. Just we will see how we proceed. Okay. So what we'll draw? First we will draw, or first we will make the adjacency cost matrix. Okay. So suppose the salesman start his journey from starting node A. Okay. So meaning is what? The salesman has to visit all remaining city, I mean B, C, D, E just once and has to come back at A. So what will be the minimum cost? Because there are so many ways to visit A to B, B to C. So out of that, the minimum distance, or we can say the minimum way to do, I mean visit all the city just once will be the consider. Okay. Okay, so just draw the how we start. We make the adjacency cost matrix. How do we make the adjacency cost matrix? Since there are 5 nodes, so we write just 5 as a column, A, B, C, D, E, column name, and similarly row name A, B, C, D, E. Distances are given. For example, A to A in the cost matrix, A to A are from same node to same node, means there is no distance, means infinite. Okay, so this will be the infinite. A to B is given 3, A to C is 1, A to D is 5, and A to E is 8. Okay, so from A to all A, B, C, D weight is like this. Similarly, from B we can see B to A 3, B to B will be infinite, B to C 6, B to D is 7, and B to E is 9. Similarly, C, D, E. Okay, we can verify C to A is 1, C to B is 6, C to C will be infinite, C to D will be 4, C to E will be 2, and from D and E. So, how we will reduce this matrix? This adjacency cost matrix must be reduced. Okay, so how we will make? So, what is called what will when it will be the reduce, if all the entries of all the rows are either infinite or at least 1 0. Okay, at least 1 0 or all infinite. If it is so, then it is reduced. If it is not so, then how we will make? So here we can say suppose the row is A, first row. Okay, so not all the entries are infinite and not even single 0, at least 1 0 is here. So it is not reduced. So what we will do? We find the minimum element. So what is the minimum element? The minimum element is 1. So we write here 1. This is the for the row reductions. Similarly here, not all the entries of second row is are 0. Are infinite, or even at least 1 0 is not in the second row. So what we will get? Minimum element is 3, this one. So we write its cost, or we can 3. Similarly here, not all entry are infinite or even at least 1 0. So we will get the minimum entry. This is 1. And similarly in D, not all are infinite or even at least 1 0 is not here. So we will get this minimum element. Okay. Similarly here, not all entries are infinite or even at least 1 0. So we will find the minimum element of this row. So minimum element will be 2, right? So this is the cost of row reductions. 1 plus 3 plus this will be the 10. So first process, this we are going. The technique is branch and bound. Okay. So after row reductions, next step is to subtract all the row element with corresponding minimum element. So subtract all first row element with 1. So infinite minus 1 is infinite, 3 minus 1 is 2, 1 minus 1 will be 0. Similarly 5 minus 1, 4, 8 minus 1, 7. So this will become. Similarly in the second row, third row, fourth row and fifth row, we will subtract with these minimum element. Okay. So we will get these element. Okay. Again we will see what this is the row reductions. We have also to check the column reductions. So what we will do? We find same thing should be in column, means all the entry of every column will be either infinite or at least 0. See here, in the first column 1 0 is there, so there is no need to reduce this column. Okay. In the second column, no, neither all entries are infinite or not even a single 0. So this has to be reduced. So what we will do? We will find the minimum element. Minimum element is 2. Okay. Similarly, In the third column, there is 0, so there is no need to reduce. In fourth column, not all entry are infinite or not even single 0. So this is not reduced. So we get the minimum and that is 1. So we will write that. Okay. And what we will do? We will subtract all the element of this column, this corresponding column with this minimum. When we will subtract, then we will get at least 1 0 and that becomes a reduced matrix. Okay. So after that, we will get this. Okay. So this will be the reduce and we can verify that either row or in the column, there will be at least 1 0 or all infinite. So here 0 case. Okay. So what will be the cost? So we have seen here in row reduction, the cost is 10. Similarly, in column reduction, the cost will be this minimum element 2 plus 1 becomes 3. So row reduction 10 and column reduction 2 plus 1 means 3. So this will be the cost of this reduced matrix. So when we'll get the reduced matrix, after that we will make the state space tree. Okay, since we have started from A, so we just write the cost from A. So this will be the cost. Total cost will be 10 plus 3, 13. So we will write the cost at here and that becomes 13. Okay. Now, so now from A, we can visit because the connectivity from every city to all other cities are there. So from A, we can visit A to B, A to C, A to D and A to E. Okay. So what we will do next? So how we will find the cost at all these and we will pick the optimal cost, I mean minimum cost node. Okay. Similarly from this way. So this is called state space tree. So same procedure will be adopted. So this becomes the reduced matrix. So let's find the cost from A to B. We would have to find the cost from A to B, A to C, A to D and A to E. So how we will do that? So just to find the cost from A to B, what we will do? First, the process is first we have to make all the entry of row A and column B as an infinite. Okay. So we can see in the reduced matrix. So A to B, we have to find the cost from A to B. So see, all the entry of row in A is become infinite. Similarly, all the entry of column B becomes infinity. Similarly, when we will find the cost from A to C, what we will do? Row A and column C entry will be infinite. So we have put, and along with that, we have also to put B to A in the reduced matrix, B to A, because we cannot traverse back. If the salesman start from A to B, so he is not allowed to visit from B to A. Okay. So the cost from B to A must also be put as a infinite. So B to A is already given infinite. Sorry, B to A is here 0. So we would also have to put this B to A as an infinite. Clear? So in further proceeding, I mean subsequent node, this process has to be adopted, right? So here A to all, A means first row, B means second column has been infinite, and one more from B to A should be marked as a infinite. Okay. So this is marked as a infinite. Now same process, I mean we have to find further, further this has to be make as a reduced matrix. Means when it will be reduced matrix, either all the row must be infinite or all the row must be infinite in a row, okay, or even at least 1 0. So first row is okay, second is not having any 0 and not all infinite. So what we will do? We will find the minimum, that is 3. Okay. Third is having 0. Yes, then it is okay. Fourth row is having 0, then it is also okay. And fifth is also having 0. So this becomes the 3. Similarly, we will have to do in the even column. The column here is 0, here all infinite, no need. Here is 0, and in that when we'll apply, I mean the reduced cost, means this becomes the 0, or already there is a 0, so there is no need to apply. Okay, so this becomes the cost. So in previous we have 13 at A, and this becomes 16. So the cost at B, I mean because we are making cost from A to B, 13 plus 3 becomes 16. Okay, so A to B will be like this. After reductions, when we subtract, I mean this, so this become, here it will be 0, rest entry will be as such. So this become A to B. The cost of reduction is 13. So how we will find the cost from A to B? So in the previous cost of A is this, A to B we have seen the 3 plus 0, because in column cost from A to B is in reduced matrix. Okay, A to B reduction cost and cost from A to B. Okay, in the reduced matrix. And which one in the reduced matrix? This one. So how we will find? Like this. Similarly, A to C. So how we will find? The row A first must be infinite. The column C should be, must be infinite, and C to A must have to infinite. Rest entry will be same as of reduced cost matrix, like this one. Okay. So A to C, same process we will adopt. We will find the minimum element. When it will be reduced, either all the entries should be infinite, or at least 1 0 should be there. Fine. So here we can see this is all infinite, this is 0 is okay. Not all entry are infinite, or not even a single 0. So we'll subtract, find the minimum, that is 1. Here it is okay, here it is okay. Okay. So after row reduction, this will become okay. Even we'll see the column. So after row reduction, there will be 0. Similarly, we will check for the column. Here is 0. Here is not 0. Okay. Because after row reduction, we have to apply the column reduction. So in the second column, there is not a single 0. So we will get the minimum element, that is 2, and subtract this. After doing this, means after row and column reduction, we will get this matrix. You can verify that. So cost of reduction will be from A to C, cost of A, that is 13, and cost of C. Cost of C is what? 1 plus 2, 3. And cost from A to C in reduced matrix. Where is the reduced matrix? This is the reduced matrix. And the A to C cost is 0. 13 plus. So again, cost from A to C will be 0. So in the state space, we will mention A to B is 16, A to C is also 16. Similarly, from A to D, we will get this. Okay. And from A to B, we will get this. Okay. So A to D, what we will do? All, I mean row A means first row will be infinite. Column D means fourth column will be infinite. And we will check whether it is reduced or not. If it not reduced, I will check either all the row must be infinite or at least 1 0. If it not so, we will find the minimum element of the row, subtract all the element of the row from that element. Okay, we will get the at least 1 0 in the row, and similarly for the column, at least 1 0 for the column. If it not so, we will get the I mean minimum element from the row and column, add them, and if it is A to D, we will also check the cost from A to D in the reduced matrix. That become the cost at D, because in state space it will be here. Okay. So A to D like this, A to E, A to D, we can see that in the second column there is not even a single 0. Here all entries are infinite, no need. Here 1 0, here 1 0, here 1 0, here 1 0. Row is already reduced. Column second column is not reduced, then we will get the minimum, subtract from that, we will get at least 1 0. So this will be the cost. So from A to D, the cost will be 13 at A and 2 plus 3. 3 is what? 3 is what? 3 is A to D. We will check the cost from A to D in reduced matrix. A to D is 3. So this will be the cost 18. Similarly, cost from A to E, you can calculate this one, 13 plus 1 plus 1. So we will get the cost from 16, 16, 18 and like this. So either we can go from A to B or A to C, because out of 16, 16, 18, 22, this will be the minimum. So if we say visit from A to B, then again the same process will be adopted. What will be the, this A to B, I mean A to B, this one matrix, reduce. So this become the reduced matrix. So this will be the base matrix from when we start from, I mean go from B to further. Okay. So this matrix will become the base matrix and A to B like this. Okay. So now what we'll see, A to B is there, then B to C, D and E, that we can go. So in state space we can, because A to B is already the C, D, E. Okay. So B to C, calculate, how we will do, calculate the cost of B to C. A to B, I mean reduced cost matrix will play as a base matrix and the same process will be adopted. Okay. We can see A to B, this one. So this will be the base matrix from ABC. Okay. So again we will find the cost at C. Okay. So this become the, what we will do, make here, now we will make the change. Okay. How we will find the reduced cost matrix from ABC, I mean from B to C, because A to B has already been done. So what we will do, we will put all the entry of row B as infinite, all the entry of column C as infinite. Okay. And we will check whether it is reduced or not. So you can see that B and C column has been there, and since we are talking about, we are visiting from B to C, so C to B is not allowed. So C to B must also be infinite. C to B has also been put infinite, because you can see that C to B infinite. Okay. So this is the way. So when we will do, we will find the cost applying the same method from A to B to, I mean B to C here. So this will become the cost. A to B to D is 16 and B to C is 19, B to D is 16 and B to E is 20. So which will be minimum? This will. So we'll move from B to D, right? Okay. So we will adopt or pick B to D. Okay. So further from D, because it has cost C equal to 16. 16 will be the minimum out of 19, 16, 20. Okay. So we will further move from D. So A, B, D already been moved. So what you can move? C and E. So now A, B, D, I mean that will be the base matrix. I mean what we have here, A, B, D, this one. So this become the, this is A to D, A, B and B to D. B to D is what, where? A to B, next A, B, D. This becomes the, okay, from D to, there could be either C or E. So this become, I mean this matrix now become the base matrix for further doing so. Okay. So here this become the base. Again what we will do, now here D to C. So again we will put all the entry of row D as infinite and all the entry of column C as infinite. You can say that all the entry from D is infinite and column C is infinite. We will check, and Since we are moving from D to C, so C to D is not allowed. So also we have to put C to D in this reduced matrix as an infinite. You can see that A, B, C, C to D has been infinite. So now we will check whether it is reduced or not. Solve the entry infinite. It is okay. It is okay. It is not okay because not all entry are infinite and not even a single zero. So this is the minimum. When we will subtract, this becomes 0. Similarly, in the column, not all the entry of first column are infinite or even at least one 0. So we will see the minimum element, that is 6, and we will subtract. Here in the second column, all entry are infinite. In third column, infinite. Fourth is also infinite. And after row reductions, this will be 0. So it will be the reduce. 0. Okay. So again, we will minimize and we will find the cost will be 6 plus 1. So this is the way. There will be 2. Okay. So cost will be 24 or 16. So it will be minimum 16. Okay. So this is the way you find. So you can see in the state space D to C and E. So here the cost we get 24, here we get 16, so which is minimum? This will be the minimum. So further we have used A to B, B to D, D to E. So all the node have except excluding C. So we will see the cost at C, and that become the 16. Okay. So this will be the sequence A to B to D to E to C. Okay. Salesman will have to visit like this way just to get the optimal cost or minimum cost. So that's all. Okay. So thank you everyone.